Okay. We learned about trigonometric substitution. The next one is a really useful and handy and important method of integration. It's integration of rational function. First, let's start with an intuition with numbers. Rational numbers are numbers such as 31 over 4, but they can be written as whole number plus a fraction. 31 over 4 can be written as 7 plus 3 over 4, which is basically the idea behind mixed fraction, which is that 31 over 4 is 7 3/4. A similar thing can be done to some rational function. Before that, well, you've seen rational function in 103. A rational function is of the form px over qx, where p and q are polynomials. We define polynomials. You have seen definitions of polynomial in 103, but I also defined it in one of your previous worksheets. Obviously, you want qx to not be 0. So right now, we'll just try to develop an intuition about what this really is. Let's look arbitrarily right now. Look at the addition of something like 1 over x minus a and 1 over x minus b. Because they are just like numbers, we make the denominator common by adding and multiplying the same thing. So now I have a common denominator, and on the top I get x minus a plus b. In fact, I get 2x minus a plus b. Note here that the degree of denominator is 2 and the degree of the numerator is 1. The degree is defined as the highest power of x. Now, looking at this in reverse, it tells us that anything that is of the form, say 2x minus a plus b, can be written as 1 over x minus a plus 1 over x minus b, and so on. And the observation is that this latter form, which is this one, is way easier to integrate than the first one, because we know that the integration of 1 over x minus a is just log, and 1 over x minus b is just log. So this gives us the idea that if we can decompose rational functions as individual fractions, they are way easier to integrate using logarithm. So get an example, x cubed plus 1 over x minus 1. Again, another thing that you may want to look back into, something that you've learned before, is polynomial division. Now here you notice that the numerator is of a higher degree than the denominator, because it's 3 and this is 1. So we perform long division. For long division, you compare the first term. So x goes into x cubed, x squared times. Then you multiply x squared with negative 1 to get the second term, which is negative x squared. Subtract, the x cubed cancels out. You're left with x squared plus x. Then you compare x squared with the x. You need an x to get that. And so on until you're left with just a number 2. What this means is x cubed plus x can be written as x minus 1 times the quotient. That's a quotient from the division plus the remainder. Okay. That's the same as with numbers, like 31 divided by 4 or 31 over 7 is 4 times 7 plus 3. Yeah, because that's 7 3/4, which means it's 4 times, it's a quotient times 7 plus the remainder. So that this entire expression becomes this, and it becomes easy to integrate. Now there are various cases that we're going to cover one by one. Let's start with the simplest case. Let f of x equals p over qx be the rational function we're dealing with. Case 1. Polynomials can be factored into linear products. Now we can write the q as a1x plus b1, a2x plus b2, so on, and there is no factor that is repeated. Then this rational function can simply be written as a1 over a1x plus b1, a2 over a2x plus b2, and so on. Okay, where the numerator is a or ax plus b, meaning it is numerator is linear. Okay, example. First of all, we're going to factor the denominator. The goal is to factor into linear terms, and we are able to do that. These are linear terms. and none of them are repeating, which means that this can be written as a over x plus b over 2x minus 1 plus c over x plus 2. That's one for each term. So if you have 3 factors, you're going to have 3 fractions. If you have 4 factors, you're going to have 4 fractions, etc. Now, because this is just a product of the denominator terms here, right? It means that you can multiply both sides by this product, which is this fraction, and you get rid of the denominators, and you end up with x squared plus 2x minus 1 on the left side. Now a has an x on the bottom, so when you multiply, the x factor gets cancelled, and you're left with 2x minus 1 x plus 2, similarly for b and c. Then you FOIL out, right here you FOIL, and you collect similar terms, meaning you collect all the x squares together, you collect all the x's together, and you collect all the constants together. Now, if these are equal, it means that the coefficients have to be the same, which means that 2a plus b minus 2c should equal 1. Similarly, 3a plus 2b minus c needs to equal 2, and the constant negative 2a needs to equal negative 1. So let's start with the simplest. Negative 1 equals negative 2a, so I get a is 1/2. Then I have 2a plus b plus 2c is 1, and 3a minus 2b plus minus c is 2. This is solving equation in 3 variables, which again you did in 103. So I'm going to solve this by elimination. I notice that I can get rid of the b by multiplying it by 2. And I do that. And then I subtract, and I get a relation between a and c. Right? But I know what a is. And a is 1/2, which means c is, so this would give me c is negative a over 5, which is negative 1/2 times 1/5, which is negative 10. Now once I find c, I can plug it into the original, on any one equation. I plugged it into this one here, I think, yeah. So 3 times 1/2 plus 2b minus negative 1/10 is 2, and you go ahead and solve, and you get value for b. Continued, which means I can rewrite this integration as integral of 1/2, 1 over x, that's a, 1/5, that's b, and 1/10, negative, that's c. And then this is easy, because this is just a bunch of log terms. Next video, we'll look at another case.